storm of questions that ignite the imagination. What would it be like to journey to the edge of a black hole, to witness firsthand the warping of space and time? The human spirit is inherently drawn to the unknown, to the mysteries that lie hidden just beyond the reach of our current understanding. Black holes, with their enigmatic nature and mind-bending implications, embody this allure of the unknown, beckoning us to explore the furthest reaches of our cosmic curiosity. Imagine a place where the laws of physics as we know them break down, where gravity reigns supreme, warping the very fabric of space and time. Picture a region where time slows to a crawl as you approach an invisible boundary, a point of no return known as the event horizon. What lies beyond this point of no return, where the gravitational pull becomes insurmountable, is a mystery that has captivated scientists and dreamers alike. The allure of black holes extends beyond their enigmatic nature, it lies also in their profound implications for our understanding of the universe. These cosmic objects, born from the death throes of massive stars, hold clues to the fundamental forces that govern the cosmos. In this exploration of the cosmos's most enigmatic objects, we embark on a journey to the edge of reality, a journey to unravel the mysteries of black holes. We will delve into the depths of these cosmic abysses, exploring their formation, their properties, and the mind-bending effects they have on the fabric of space-time. Our journey will take us from the familiar realm of stars and galaxies to the uncharted territories of theoretical physics, where scientists grapple with the implications of black holes for our understanding of the universe. We will explore the concepts of warped space-time, gravitational lensing, and spaghettification, the stretching of objects due to intense tidal forces near a black hole. Prepare to have your perceptions challenged, your curiosity piqued, and your imagination ignited as we venture into the heart of darkness, to the very edge of reality, to unlock the secrets of black holes. In the vast cosmos, black holes stand as enigmatic sentinels, born from dying stars, defying our understanding of space, time, and gravity. These cosmic abysses, where gravity's grip is relentless, warp space-time beyond recognition. Einstein's theory of general relativity explains their existence, changing our understanding of gravity. Imagine a trampoline with a bowling ball creating a dip, representing space-time curvature. A black hole, like an incredibly dense object, punches through the trampoline, distorting space-time. Section 2, Stellar Demise, the birth of a black hole. The life cycle of a star is a captivating tale of birth, evolution, and eventual demise. Smaller stars fade into white dwarfs, cooling over billions of years, while massive stars meet a dramatic end, giving rise to black holes. Section 3, the point of no return, the event horizon. As we venture closer to a black hole, our journey takes us to a boundary of paramount significance, a point of no return known as the event horizon. This invisible barrier, a cosmic Rubicon, marks the point at which gravity's grip becomes inescapable, where not even light, the fastest entity in the universe, can muster the energy to escape the black hole's clutches. Imagine approaching this invisible boundary, the event horizon looming ahead, a silent sentinel marking the edge of the abyss. As you draw closer, the curvature of space-time becomes increasingly pronounced, warping your perception of the universe around you. Time itself, once a reliable constant, begins to dilate, slowing down as you approach the event horizon, a consequence of the intense gravitational field. To an outside observer, watching from a safe distance, your approach toward the event horizon unfolds in slow motion, your image stretched and distorted by the extreme gravity. As you inch closer to the point of no return, your image would appear to freeze in time, red shifting into oblivion, the light from your vessel struggling to escape the black hole's gravitational grasp. However, from your perspective, as you plunge headlong into the abyss, the experience would be markedly different. You would continue to hurtle toward the event horizon, blissfully unaware of the strange and wonderful phenomena unfolding behind you. Time for you would continue to flow normally, at least for a while, as you journey deeper into the black hole's gravitational well. Section 4. A tapestry of black holes. Types and classifications. Black holes, far from being monolithic entities, exhibit a remarkable diversity, a cosmic tapestry woven from the threads of stellar evolution and galactic dynamics. These gravitational behemoths scattered throughout the universe are classified into distinct categories based on their mass, their origins, and the environments in which they reside. At one end of the spectrum, we have stellar mass black holes, the remnants of massive stars that have met their demise in spectacular supernova explosions. These black holes, typically a few times more massive than our Sun, are sprinkled throughout galaxies, their presence often betrayed by the gravitational dance they engage in with companion stars. Venturing into the realm of galactic centers, we encounter supermassive black holes, the true titans of the cosmos. These gravitational behemoths, millions or even billions of times more massive than our Sun, lurk at the hearts of galaxies, their immense gravitational pull influencing the motions of stars and gas on a galactic scale. Bridging the gap between stellar mass black holes and their supermassive counterparts are intermediate mass black holes, a class of objects less well understood but thought to play a crucial role in galactic evolution. These black holes, ranging in mass from hundreds to thousands of times the mass of our Sun, are believed to form through the mergers of smaller black holes or the runaway collapse of dense star clusters. Our journey toward the heart of a black hole begins at a safe distance, far from the event horizon, where the fabric of space-time, though subtly warped by the black hole's immense gravity, still retains a semblance of normalcy. As we venture closer, however, gravity's grip tightens, its influence on our surroundings becoming increasingly apparent, a cosmic waltz between our spacecraft and the unseen behemoth that lies ahead. Imagine peering out of the viewport of our hypothetical spacecraft, the inky blackness of space dotted with the distant glimmer of stars. As we approach the black hole, this celestial tapestry begins to distort, the stars appearing to shift and swirl around a central point, their light bending and warping under the influence of the black hole's intense gravitational field. This warping of spacetime, a direct consequence of Einstein's theory of general relativity, is not merely a visual illusion. It is a fundamental alteration of the very fabric of the cosmos, a cosmic dance between mass and energy, where gravity dictates the rhythm of motion. As we draw closer to the black hole, this dance becomes more frenetic, the curvature of space-time increasing exponentially, pulling us inexorably toward the abyss. Our spacecraft, caught in this gravitational maelstrom, would begin to accelerate, drawn toward the black hole like a moth to a flame. This acceleration, however, is not uniform, rather it is differential, meaning that the side of our spacecraft closer to the black hole experiences a stronger gravitational pull than the side farther away. This difference in gravitational force, known as a tidal force, would have profound and unsettling effects on our journey. Our journey toward the heart of a black hole begins at a safe distance, far from the event horizon. As we venture closer, gravity's grip tightens, its influence on our surroundings becoming increasingly apparent. Imagine peering out of the viewport of our hypothetical spacecraft, the inky blackness of space dotted with the distant glimmer of stars. As we approach the black hole, this celestial tapestry begins to distort, the stars appearing to shift and swirl around a central point, their light bending and warping under the influence of the black hole's intense gravitational field. This warping of space-time, a direct consequence of Einstein's theory of general relativity, is not merely a visual illusion, it is a fundamental alteration of the very fabric of the cosmos, a cosmic dance between mass and energy. As we draw closer to the black hole, this dance becomes more frenetic, the curvature of space-time increasing exponentially. Our spacecraft, caught in this gravitational maelstrom, would begin to accelerate, drawn toward the black hole like a moth to a flame. This acceleration, however, is not uniform. Rather, it is differential, meaning that the side of our spacecraft closer to the black hole experiences a stronger gravitational pull than the side farther away. This difference in gravitational force, known as a tidal force, would have profound and unsettling effects on our journey. As we venture deeper into the gravitational well of the black hole, our surroundings take on an increasingly surreal and disorienting quality. This phenomenon, known as gravitational lensing, warps space-time and our perception of the universe. Imagine a distant galaxy, its light bent and distorted by the black hole's intense gravity. This lensing effect magnifies and distorts light from stars and galaxies, creating a cosmic lighthouse. Gravitational lensing is a powerful tool for astronomers, revealing the universe's hidden secrets. As our spacecraft plunges deeper into the black hole's gravitational embrace, the tidal forces, those invisible hands of gravity pulling at different parts of our vessel with varying strengths, become increasingly extreme, stretching our spacecraft and its occupants like cosmic taffy in a process aptly named spaghettification. Imagine, if you will, our spacecraft, once a sturdy vessel designed to withstand the rigors of interstellar travel, now caught in a gravitational tug-of-war, the side closer to the black hole being pulled with exponentially greater force than the side farther away. This difference in gravitational pull, this tidal force, would have devastating consequences for our spacecraft and its hypothetical crew. Initially, the effects of spaghettification would be subtle, a slight stretching sensation, a feeling of being pulled in two directions at once. As we drew closer to the event horizon, however, these forces would intensify, stretching our spacecraft into an elongated shape like a strand of spaghetti, hence the name. The human body, far more fragile than our hypothetical spacecraft, would fare even worse in this cosmic tug-of-war. Imagine the sensation of your feet being pulled with a force thousands, millions, or even billions of times stronger than your head, your body stretched and elongated, your bones cracking and snapping under the strain. Spaghettification, while a gruesome thought experiment, highlights the extreme nature of gravity near a black hole, where the very fabric of space-time is warped to its breaking point, where the familiar laws of physics as we know them cease to apply. As we approach the event horizon, the point of no return, time itself falls under the sway of the black hole's immense gravity, warping and distorting our perception of its passage. Imagine glancing at the chronometer, its steady ticking a reminder of time. As we draw closer, the ticking slows, the seconds stretching out, each tick a labored effort against gravity. This temporal distortion is a fundamental consequence of general relativity. Einstein's theory predicts that time is relative, its passage dependent on gravity. To an outside observer, our spacecraft would appear to slow down, its movements becoming sluggish, like a film reel playing slowly. As we reach the event horizon, our image would appear to freeze, frozen in a perpetual state of falling, our light struggling to escape. From our perspective, time would continue to flow normally, at least for a while. We would be unaware of the strange temporal distortions, our perception of time remaining consistent. Our journey to the heart of a black hole culminates at the event horizon, that invisible boundary marking the point of no return, a cosmic Rubicon beyond which even light, the swiftest entity in the universe, cannot escape the relentless pull of gravity. Imagine our spacecraft stretched and distorted by tidal forces, time itself warped and dilated, approaching this invisible barrier, its presence marked not by any visible signpost but rather by the inexorable grip of gravity, pulling us ever onward. As we cross the event horizon, the universe outside, once a tapestry of stars and galaxies, fades from view, the light from those distant objects no longer able to reach us, trapped within the black hole's gravitational prison. What lies beyond the event horizon, the realm within the black hole's grasp, remains one of the greatest mysteries of modern physics. Some theories suggest that we would continue to fall inward, our spacecraft eventually crushed to an infinitesimal point at the singularity, the heart of the black hole, where density and gravity become infinite. Other theories propose more exotic possibilities, such as wormholes, hypothetical tunnels through space-time connecting distant points in the universe, or even the possibility of emerging into a different universe altogether. These theories, while intriguing, remain highly speculative, the true nature of what lies beyond the event horizon, a subject of ongoing scientific inquiry and debate. Having crossed the event horizon, the point of no return, we find ourselves irrevocably drawn into the black hole's enigmatic embrace, our spacecraft, now a mere plaything of gravity, hurtling toward an unknown fate. Behind us, the universe we once knew recedes from view, the light from distant stars and galaxies unable to penetrate the event horizon's veil, leaving us in a realm of darkness and mystery. Imagine, if you will, peering out of the spacecraft's viewport, the familiar tapestry of stars replaced by an all-consuming blackness, a void so profound that it seems to defy description. Our instruments, once beacons of scientific precision, now flicker and sputter, their readings nonsensical, overwhelmed by the extreme conditions surrounding us. As we descend deeper into the black hole's gravitational well, the curvature of space-time becomes increasingly extreme, warping our perception of reality, distorting our sense of direction and distance. The very fabric of space and time, once thought to be immutable, now twists and turns like a cosmic contortionist, its movements dictated by the black hole's immense gravitational pull. Our spacecraft, caught in this maelstrom of warped space-time, would likely be subjected to tidal forces far beyond anything imaginable in the universe we left behind. The very atoms that make up our vessel, once bound together by the strong nuclear force, would begin to feel the strain, their bonds stretched and contorted by the relentless pull of gravity. Our journey into the heart of the black hole inevitably leads us to the singularity, that enigmatic point at the center of the abyss where, according to our current understanding of physics, gravity's grip becomes infinitely strong, crushing matter and energy into a point of zero volume and infinite density. Imagine, if such a thing is even possible, all the matter that ever fell into the black hole, from the first primordial particles to the remnants of stars and planets, compressed into an infinitesimally small point, a cosmic needle in the haystack of space-time. At the singularity, the laws of physics as we know them break down, our equations yielding nonsensical answers, our models unable to cope with the extreme conditions. The singularity, often depicted as a point of infinite darkness and silence, might be better envisioned as a cosmic inferno, a crucible where matter and energy are constantly being ripped apart and reassembled in ways we can scarcely comprehend. The very fabric of space-time, already stretched and distorted beyond recognition, would likely unravel completely at the singularity, its threads torn apart by the relentless pull of gravity. What happens at the singularity remains one of the biggest mysteries in modern physics. Some theories suggest that matter and energy are completely annihilated at the singularity, their information lost forever to the universe outside. Others propose that the singularity might be a gateway to other universes, a cosmic portal through which matter and energy can escape the black hole's clutches. The extreme conditions within a black hole, where gravity reigns supreme and the laws of physics as we know them break down, have led some physicists to speculate about the possibility of wormholes, hypothetical tunnels through space-time connecting distant points in the universe or even different universes altogether. Imagine, if you will, a shortcut through the cosmos, a tunnel through the fabric of space-time that could transport you across vast distances in an instant, bypassing the limitations of speed and distance imposed by conventional travel. Wormholes, once relegated to the realm of science fiction, have captured the imaginations of physicists and laypeople alike, offering the tantalizing possibility of faster-than-light travel and exploration of the universe on a scale never before imagined. The concept of wormholes arises from Einstein's theory of general relativity, which describes gravity not as a force but rather as a curvature in space-time caused by the presence of mass and energy. Just as a bowling ball placed on a trampoline creates a dip in the fabric, massive objects warp the fabric of space-time around them. Theoretically, if enough mass and energy were concentrated in a small enough region of space-time, it could create a tunnel-like structure connecting two distant points, a cosmic shortcut known as a wormhole. However, the creation and stability of such wormholes would require exotic forms of matter with negative energy density, something that has never been observed in the universe. One of the most perplexing questions facing physicists is the fate of information that falls into black holes. According to quantum mechanics, information cannot be destroyed, only transformed. But black holes seem to swallow information forever. This paradox has puzzled physicists for decades. The holographic principle suggests information is encoded on the event horizon. This principle preserves information, even as particles fall into the black hole. Section 5. Echoes from the Abyss, Unraveling the Mysteries Within. Physicists study black holes by observing their interactions and developing theoretical models. Gravitational waves predicted by Einstein reveal black hole properties. Accretion disks emit radiation, helping infer black hole characteristics. The Event Horizon Telescope captured the first image of a black hole's shadow. Section 1. The Black Hole Engine, Harnessing Cosmic Power. As we stand on the precipice of a new era of space exploration, our gaze drawn ever onward by the allure of the cosmos's greatest mysteries, we find ourselves contemplating the seemingly impossible, harnessing the immense power of black holes, those cosmic engines of creation and destruction, for the benefit of humankind. Imagine, if you will, tapping into the energy released by matter as it spirals into a black hole, its very essence converted into radiation via the friction of an accretion disk heated to millions of degrees. This energy, released in the form of light and heat, could potentially power entire civilizations, its sheer abundance dwarfing even the most ambitious fusion power projects envisioned here on Earth. One theoretical approach to harnessing black hole energy involves the Penrose process, proposed by physicist Roger Penrose, which exploits the rotational energy of a spinning black hole. Imagine a particle entering the ergosphere, a region of spacetime near a rotating black hole, where objects are forced to rotate with the black hole, even light itself. This particle, carefully chosen and directed, could be split in two within the ergosphere, with one half falling into the black hole while the other escapes, carrying with it more energy than the original particle possessed. This extracted energy drawn from the black hole's rotation could then be harnessed for our own purposes. Another theoretical approach involves manipulating the magnetic fields that thread through accretion disks, generating powerful electric currents capable of powering entire star systems. These magnetic fields, twisted and amplified by the black hole's rotation, act like cosmic dynamos, converting the kinetic energy of infalling matter into electromagnetic energy. Section 2. Building the Impossible Spacecraft of the Future. Imagine a spacecraft of exotic materials withstanding black hole forces, using advanced propulsion systems to warp spacetime. Shielding from intense radiation and using quantum entanglement for communication, this vessel would be a marvel of engineering. Section 3. Beyond the Event Horizon, a New Era of Exploration. Imagine a mission beyond the event horizon, venturing into the heart of a black hole, uncovering cosmic secrets. Such a journey would be the pinnacle of human exploration, driven by our insatiable curiosity. Some speculate black holes might be gateways to other universes, realms beyond our wildest dreams. Contemplating such a journey showcases the boundless potential of the human spirit. Section 1. Black Holes, Beacons of Cosmic Wonder. As we conclude our exploration of these celestial abysses, we find ourselves humbled by the sheer scale and mystery of the universe we inhabit. Black holes, once relegated to the realm of theoretical speculation, have emerged as tangible proof of the universe's capacity to astound, to challenge our understanding, and to ignite our imaginations. They stand as beacons of cosmic wonder, beckoning us to delve deeper into the mysteries of the cosmos, to push the boundaries of human knowledge, and to unravel the secrets woven into the fabric of spacetime. From the death throes of massive stars to the hearts of galaxies, black holes play a pivotal role in shaping the cosmic landscape, their influence felt across vast stretches of space and time. They are the architects of galaxies, their gravitational pull sculpting the orbits of stars and gas clouds, driving the evolution of these vast cosmic structures. Black holes are also the ultimate laboratories of physics, their extreme environments testing the limits of our understanding of gravity, quantum mechanics, and the very nature of reality itself. They challenge our preconceived notions about space, time, and the relationship between matter and energy, forcing us to confront the limitations of our current knowledge and to seek out new theoretical frameworks to explain their enigmatic behavior. Section 2. An enduring enigma. Despite decades of study, black holes remain mysterious, their true nature eluding us. The singularity challenges our understanding, a cosmic question mark. The information paradox sparks debate among physicists. Some argue information is lost forever, while others propose it is encoded on the event horizon. Wormholes remain a tantalizing yet theoretical prospect. As we peer into these cosmic abysses, we are reminded of our vast ignorance. Black holes serve as a reminder that our journey of discovery is far from over. The universe still holds countless secrets waiting to be unveiled.